Okay, so today we are happy to have Tara, who will tell us about equivariant cohomology and the symplectic Diffeotype of complexity 1 for manifolds.
Thank you, and thanks. It's nice to connect with everyone today. I'll talk about today some joint work with Liat Kessler and some work with Liat and Sue Tolman that's taken place over the last several years. And I have to share my gratitude to the National Science Foundation for their support over the years. It's a depressing moment in the US for science funding. So we still have to, anyway, so there we are. So an overview, I want to talk today about the relationship between the geometry and topology of Hamiltonian circle actions on four manifolds, and the relationship to what combinatorial data we have to represent those and how you can go backwards and forwards. The main point, so the work that Liat and I did in our two papers was to eventually produce a generators and relations description of the equivariant cohomology ring. And the way this worked, it sort of went by way of thinking about how toric actions, what happens with toric actions, and also I'll define all these words and show you how everything works, and then thinking about how that should work in the complexity 1 setting. And then once you have that description, the question is, what does that presentation determine? And with the risk of ruining the punchline, the answer is that it determines for four Hamiltonian circle actions on symplectic four manifolds. It determines the equivariant diffeotype of the manifold, but not necessarily, certainly not the symplectic structure. And we'll see already in the toric case that the symplectic structure is quite flabby with regard to equivariant cohomology. And then it also doesn't determine complex structure. And so I'll give some examples about what exactly does happen. And I should say, I'll monitor the chat for questions, but also please do interrupt. Okay, so that's the big overview. So our setting, our framework, we have a symplectic form, a closed two form, non-degenerate, our manifolds orientable, and we have lots of examples. So these examples, we're going to draw on these. I'm particularly going to draw on toric varieties. I should use a different color maybe to make this clear. So I'll particularly say quite a bit about toric varieties and take inspiration from those. So toric varieties have sort of two different representations. The symplectic geometers, and I'll describe exactly how this works. Think about these in terms of convex polytopes. But the algebraic geometers like to describe these in terms of combinatorial gadgets called fans. And the information about the sort of geometry of the toric varieties is contained in this data. So the fan, you can reconstruct a fan from a convex polytope by taking the rays of the fan to be the inward pointing. Yes, I took inward pointing normal vectors to the facets of the polytope and then choosing a cone whenever a collection of facets intersects non-trivially. And from the fan, you can construct the combinatorial type of the polytope, but not necessarily the size. And so if I take a slightly bigger polytope with the same shape, that bigger turquoise polytope will produce, oops, that's not what I meant to do, will produce the same fan as the smaller green one. So but the bigger polytope has a different symplectic structure. So that's sort of captured in the combinatorics. Okay, so the corner of symplectic geometry that I work in is in the context of Hamiltonian actions. So we say an action is Hamiltonian if it admits an equivariant momentum map. So a momentum map is something that satisfies, it sort of puts together all of the Hamiltonian, it requires that the group action be generated by Hamiltonian vector fields, and that the Hamiltonian functions corresponding to the Hamiltonian vector fields fit together nicely. So the Hamiltonian vector fields show up as, if I have an element of the Lie algebra, then I can exponentiate that into the group and look at how that one parameter subgroup of G is acting on M. And so this is at some point in M, and then I can differentiate that at t equals 0. And this is a tangent vector to the manifold at M. So I'll call this xc at P. And the Hamiltonian condition tells us that if I take that vector field and plug it into the first coordinate of the moment map, this of the symplectic form, this is still a closed one form, and Hamiltonian Hamiltonicity requires that this be exact. So this is d of something, and this phi is the Hamiltonian function. And what we require for the momentum map is, so the momentum map puts all of these together. A point P is mapped to a map from G to R, and it is going to take a C to XC of P. And so we require that these fit together as a function from M to the dual of the Lie algebra. And let's see, this equivariant condition is equivariant with respect to the G action here and with respect to the coadjoint action here. Okay, so this is sort of standard bread and butter in the equivariant side of symplectic geometry. And the point that I wanted to make here is that this is a quote unquote soft tool, which means that it's related to sort of it's related to Morse theory in the sense of Bott. These component functions, these Hamiltonian functions are, this is a Morse function on M in the sense of Bott. So meaning that it might have critical submanifolds, not just critical isolated critical points. And you have a bit of control over the critical set. These are the stationary points for the vector fields, for the corresponding Hamiltonian vector field. So it's the fixed set of this one parameter subgroup, X of TC. And so this momentum map is one of the tools that's been around in symplectic geometry for decades, and it is it's one of the tools that we use to study symplectic Hamiltonian actions. Okay, so one of the very first results. This is a result from the 60s relating symplectic actions, relating the existence of such a moment map to fixed point sets. So Frankel showed in the 60s that if you have a circle action on a Kähler manifold, so this is in the context where we have a symplectic form and a compatible complex integrable complex structure. So we have a compact Kähler manifold. And we're assuming that we have a circle action that preserves the symplectic form. So S1 is so the pullback of the symplectic form under the action stays is equal to omega. Then this action is Hamiltonian precisely when you have fixed sets. when your fixed point set is not empty. So this is giving some indication that fixed points play some important role. And this result was explored further. So Frankel was looking specifically at the Kessler case. Duce and McDuff then went on to look at the symplectic case. So in general, if you have a Hamiltonian circle action on a symplectic four-manifold, not necessarily Kessler, then this symplectic action is this result still holds. The action is Hamiltonian still, if and only if there are no fixed points. And what she proved in higher dimensions is that this is no longer true in the pure symplectic category. So there are 6 manifolds and higher dimensional manifolds with with symplectic circle actions that are not Hamiltonian. So McDuff produced these examples. These examples, the example that McDuff first produced had fixed surfaces. And later, Tolman and Zhang have produced examples of symplectic circle actions that have only isolated fixed points. So they sort of have the minimum possible fixed points, and they still are symplectic actions that are not Hamiltonian. And sort of the way these work, if your action is symplectic, you can produce something like a moment map, but it's circle valued, and the action is Hamiltonian only if you can sort of lift the moment map from the circle to the universal cover, and that doesn't happen. And Tolman and Zhang have these optimal examples, I think, where they just have. Ooh, I'm going to get it wrong. I want to say they just have 2 fixed points, but I think they have to have. I'm going to get it wrong, so I'm not going to say. Okay, so in any case, they have optimal examples. Okay, so another, so now shifting back to the, so that was sort of a digression about actions that are Hamiltonian, are symplectic, but not necessarily Hamiltonian. Now I want to restrict to, so here we're looking at Hamiltonian actions. And I want to restrict to abelian groups. So if I have a torus, a compact torus, a product of n circles, acting on a 2D dimensional compact, I'm going to be going back and forth between compact and non-compact, but I'll typically be thinking about compact examples. And I'm assuming this is Hamiltonian, so I have a momentum map to the dual of the Lie algebra of the torus, so that is isomorphic to Rn. In the 80s, Atiyah and independently Gilliman and Sternberg proved that one of the key properties of the momentum map is that the image is a convex polytope. And more explicitly, it's the convex hull of the images of the fixed points. So here, again, we're seeing that the fixed points play some key role. And what I want to say is Atiyah's proof develops and relies on Morse theory of components of the momentum map. And so at the end, you're left with the question, what does this momentum map image tell you? What does this convex polytope, what can you recover from the convex polytope about the T action on M? And again, because the sort of the lingo is that these are soft tools on M rather than hard holomorphic tools that are telling you something about complex structures. Okay, so a key fact, assuming that this torus action is effective, a key fact is that the rank of the torus that is acting is at most half the dimension of the manifold. And the reason for this is the vector fields at a generic point so a point on which, so at a generic point, the vector fields, if I choose a basis here of cotangent vectors or identically tangent vectors, then I can look at the vector fields that they generate. Actually, I shouldn't put them there. I don't want them there. I want them in the dual of the Lie algebra. So if I take a basis of the Lie algebra, then the vector fields xc1 at some point up to xcn. These are part of a symplectic basis of TPM, by which I mean they are pairwise. They are pairwise 0. So omega of x c I of p x c j of p is 0. And we know, so this is, they span an isotropic, actually, so that's what I should really say. They span an isotropic subspace of TPM. And so they can span at most half the dimension of the manifold. Okay, so, and when n is equal to d, we call this action toric. We call this a toric symplectic manifold. And these, in the toric case, the momentum polytope tells you everything. So in the toric case, Delzant proved that there's a one-to-one correspondence between Hamiltonian, and I should be very explicit here, n tori on M2n, acting on with momentum image, and these are classified entirely by a certain class of polytopes. Let's see, so simple means that the polytope has n edges emanating from each vertex. Rational means that the edges point in lattice directions. And smooth means that at a particular vertex where I have n lattice vectors coming out of the vertex, these are a z basis of the Zn lattice. Okay, so this is a very special class of polytopes in Rn. And I should also say for this theorem, this is a one-to-one correspondence up to, I have to say what up to is. So over here, this is up to equivariant symplectomorphism. And on the right-hand side, this is up to, so a polytope in Rn, I can translate it around. That amounts to adding a constant to the momentum map, which doesn't change the Hamiltonian criterion. So this is up to translation in Rn. And then I can also choose lattice equivalent polytopes. So it's also up to SLN Z. So translations. So up to this is maybe called affine equivalence. Okay, so that is the symplectic classification of toric manifolds. And what I should say, a word about the proof. So in one direction, you associate to such a T you simply associate the polytope. And in the other direction, given a polytope, so given some polytope, say in R3, I can construct a symplectic manifold whose moment image is this polytope. And the way this construction goes is you construct, let's call this delta, you construct an M delta as I take an affine, I take a vector, a symplectic vector space, C to the D, where D is the number of facets of the polytope, and I mod out by a subgroup. K is a subgroup of TD. So the complex vector space has D circles acting by coordinate-wise multiplication, and the combinatorics of the polytope tells me how to cut out an abelian subgroup to use to take a symplectic reduction, and I should be careful at some value alpha by K. And so again, it is the combinatorics of delta that tells me how to choose K and how to identify the regular value where I want to reduce. So I'm not going to say too much more about symplectic reduction unless people have questions, but I think a lot of people here are quite familiar with this, and it's a quite beautiful, very explicit construction for those who aren't. Oh, okay. So this summarizes what I just said. So so this classification is up to equivariant symplectomorphism on the one hand, up to affine equivalence on the other side, and I have this way of producing a symplectic quotient ON is the same as D on the previous slide. Okay. From there, there is a theorem, and this is really in the algebraic geometry literature, or the combinatorics literature, depending on your view on this. But because so I can produce this manifold as a symplectic reduction, but it is also a GIT quotient. Geometric invariant theory quotient in algebraic geometry, and from that perspective, that's where Danilov and Jerkovich were really coming from. But their theorem, you can also give a nice description in the symplectic category. So they give a very nice description. They say that the equivariant cohomology of this manifold can be described over the integers as a polynomial ring, where I have here, I really did use capital N instead of D. So here, this N is the same. So I have N variables, one for each facet in the polytope. So my polytope delta has facets F1, up to Fn. And so I have n variables, and the relations in this ring are simply that whenever I have a collection of facets that do not intersect, then I throw in that monomial into an ideal. We'll call this I. And so this is the face ideal. This description is sometimes called the face ring description of the for the polytope. And Danilov and Yurkovich proved that this was this describes the equivariant cohomology. These xi, so when you're thinking of this, so these xi are in degree 2, and they are all Chern classes of certain natural line bundles that arise by thinking of this as a quotient of a vector space. Another, let me see my, where am I? Okay, so another way to think about this is symplectically. So when we take a symplectic reduction, Francis Kirwan's work tells us that we have a map from the equivariant cohomology of M, the equivariant cohomology of the total space of the quotient, so HT n of Cn. We have a map to the cohomology of the level set that lets us define the quotient. And Kirwan proves that this is surjective. And there's further work of Tolman and Weitzman that lets us compute the kernel of this. And they both of these results are much more general about symplectic reductions. And putting these together, so when we're in the very special case of a toric variety, this ring is precisely the numerator that we see in the Danilov-Jerkovich theorem, and the kernel that, if you follow through the calculations, the kernel of this map is precisely this monomial ideal. Okay, so that's a symplectic view on this, and there's a lot is known about the algebraic structure of equivariant cohomology rings for Hamiltonian torus actions, and so in particular, there's a surjection from equivariant cohomology to ordinary, and the kernel just consists of linear terms in I. This is equivalent to this is encoded in the algebra structure. So what I should say is equivariant cohomology is a ring, but it's also an algebra over a polynomial ring. And this algebra structure is precisely the thing that you have to kill. So that shows up when you're trying to understand the ordinary cohomology of the manifold. What this is used for. So I said that this sort of shows up in algebraic algebraic geometric literature and in combinatorial literature. Some of where this has been used historically, Balera and Lee, and then Stanley used this they used this description of the cohomology ring to say some things about this ring, knowing that it's the cohomology of a complex projective variety. So Stanley proved that this ring, these face rings, have nice combinatorial properties. And those nice combinatorial properties come from Poincare duality in a cohomology ring. So Betty numbers being symmetric, and also the growth rate of the ring, of the degrees of the size of the degree k pieces, is somewhat controlled, and so that is a consequence of, in this context, the Hard-Lefschetz theorem. And so things that we sort of take for granted as topologists have nice properties for combinatorics of face rings. Another piece of information, and this gets at the original question that I was asking, what does, I guess what we can see in this Danilov-Jerkovich theorem is that this cohomology ring is completely determined by the polytope. It just depends on the combinatorial structure of the polytope. And what Masuda did, he proved that this ring, from this ring R, from this Danilov-Jerkovich description, you can almost reconstruct M. And what I mean here is this has to be, you have to know the ring as an algebra. So I was mumbling about the algebra structure, and understanding that algebra structure is really essential in this proof. The reason that it's essential, you can see quite quickly, just looking at this ring without understanding any more. If I just said, so this is just monomials that are products when faces don't intersect. The same ring, you will get the same ring if you look at a, if your polytope is a rectangle. So in that case, I'm going to have 4 generators, and I'll have 2 relations. X1 and X3 don't intersect, and X2 and X4 don't, F2 and F4 don't intersect. So I'll have 2 relations, X1, X3, and X2, X4. And I will get exactly the same face ring if I look at the polytope that is a trapezoid. Those are both perfectly reasonable quadrilaterals that satisfy simple, smooth, rational conditions. But one is the rectangle corresponds to the symplectic manifold S2 cross S2, and the trapezoid corresponds to the Hirzebruch surface H1. This is also known as the blowup of CP2 at one point. Those 2 manifolds are both S2 bundles over S2. One is a trivial S2 bundle over S2. The other is a non-trivial bundle, the non-trivial bundle. So these are the 2 different possible S2 bundles over S2 as smooth manifolds. And so we know they can't be, we know they are not, it is known that they are not diffeomorphic, but they have precisely the same face ring. So what Masuda shows is, if in addition, you know the algebra structure does distinguish these 2 polytopes. And he needs some additional information, although I think in 4 dimensions it's small enough that you actually don't need that extra information. And but if you have this ring as an algebra and the Chern class, from that you can reconstruct the polytope and or the fan. Actually, no, sorry, not the polytope. Precisely not the polytope. You can reconstruct the fan. He can't reconstruct. It's impossible to reconstruct just from the cohomology ring, the symplectic structure. But then you can reconstruct the manifold up to diffeomorphism. So of course, for S2 cross S2, there are infinitely many symplectic structures. I can make the rectangle much wider or much shorter or taller, and the polytope and the cohomology ring never see that. But that's the combinatorial manifestation of the symplectic structure. Okay, and I think think that is what I wanted to say so far about toric symplectic manifolds. Are there questions? I think a lot of this at this point, a lot of people will have been very familiar with. So I hope that this is good. Okay. There's an alternative description of this cohomology ring. So the face ring description, what I should say, this description in terms of generators and relations, this is the description that people try to generalize in other contexts because this is quite amenable to computation. So I'll say in a second what I mean by that. But there is an alternative description. You can also describe the equivariant cohomology of a Hamiltonian T-space often, and certainly in the case of toric symplectic manifolds, as a subring. So here this is a quotient ring, but you can also describe it as a subring of a direct sum of polynomial rings, one for every vertex of the polytope. This relies on work of Francis Kirwan, also of Tolman and Weitzman, and on the algebraic side of Goreski, Kottwitz, and McPherson. And I'm not going to go too deep into the details, other than to say that this description exists, and it is it's valuable because it helps you establish certain properties of cohomology rings that are perhaps less obvious from the quotient ring construction. On the other hand, the quotient ring construction, as I said, is more amenable to computation, by which I mean the computer algebra packages that algebraic geometers frequently use, or that are adapted precisely for quotient rings. So Macaulay 2, for example, works very well for quotient rings, and it really hates subrings. So so pluses and minuses. Okay, so this what I've been talking about for the last 20 minutes or so is all talking about this setup of what happens in the toric case when the torus acting on your manifold is exactly half the dimension. You can relax this slightly and ask what do we know from the toric case? Is what we know from the toric case still true? And in this case, you can ask about a torus that's one less than half the dimension. We'll call this complexity 1. This 1 is this 1. And you can ask about complexity k in general. So if you have d minus k acting on a 2D manifold. Complexity 1 will be where we live today. So in this case, this is the trivial group acting on a surface, on a 2-manifold. A circle acting on a Hamiltonian circle, a circle acting in a Hamiltonian fashion on a 4-manifold, a 2 torus on a 6-manifold, and so forth. The case of a Hamiltonian circle action on a 4-manifold, these were classified by Carchon in terms of decorated graphs. This builds on earlier work of Michel Audin, Ahara, and Hattori. But I'm going to be mostly referring to Carchon's work because that's the thing that I use with Liat and with Liat and Su. The decorated graph has vertices and edges as before. The vertices in this case have to be identified as big or small, basically. So the big ones, big vertices, correspond to fixed surfaces. So one of the nice things in the toric case is that all of the fixed points are isolated. When we're in the complexity 1 case, we can have isolated fixed points, or we can have codimension 1 fixed sets. Those are complex codimension 1, and so the small vertices correspond to isolated fixed points. And the goal is to classify these up to symplectomorphism. So the data that you need to remember, this is basically what Carchon classifies. These These decorated graphs have labels that tell you about isotropy weights. The big vertices have labels that tell you, so these are fixed surfaces, these have certain genus. They have a symplectic area. And everywhere I should have momentum map labels. So if I want to reconstruct the manifold up to symplectomorphism, I need to be able to see those symplectic sizes. And that's the same in the toric case as being able to distinguish a little square from a big square. Okay, so those were classified. And higher dimensional ones have been classified, at least in the tall case, and I think the rest of the classification continues and is in progress. I can't remember the final state if everything is on archive or not, but there is a tall case that is published and in the literature, and then there is the non-tall case. And these are classified much in the same way. They're classified by the moment image and a painting of the moment image, which consists of combinatorial and homotopic data. The key thing is that again, we still have big vertices and small vertices corresponding to isolated and surface fixed sets, and then we have a lot of additional information. Okay. So to achieve some sort of to prove my eventual theorem, I need to make again a detour through equivariant cohomology of these things. And the very first thing that Liat and I did was to generalize this subring version of the equivariant cohomology calculation. This relied on earlier work of mine with Rebecca Golden in the case when you have a complexity 1 manifold with only isolated fixed points. And if you have fixed points and surfaces, the computations are just a little more annoying, but they're still possible to do. And so, yeah, so that's that. And Liat and I used this to provide a generators and relations description in the case of complexity 1 actions on 4 manifolds. So what I should note here is this is in all dimensions. But this is specifically for the 4 manifolds. And we were quite explicit in what we proved. So what we then were able to prove, so this is using generators and relations. We were able to classify all of the possible, well, we were able to, from the equivariant cohomology, so the theorem, this is the first theorem, says this, that the following things are equivalent, that the dull graphs, oh shoot, didn't tell you what the dull graph was. Ah, right, we had a decorated graph from Carchon. The dull graph, the decorated graph had to contain all of the moment map information that is what tells you the symplectic structure in the end. The dull graph basically forgets that. And that is, as we saw in the toric case, we don't expect equivariant cohomology rings to be able to identify symplectic sizes, and so we forget that information. And once you forget that, then we have dull graphs having forgotten symplectic information. We prove that the dull graphs are the same if and only if these cohomology rings are isomorphic. Oh, and I should say as algebras, modules or algebras, however you want to think about it, over the equivariant cohomology of a point. This is this is really a condition on the even part of the cohomology, and we need the odd part to be the same. The odd part, I'm not going to go into too many details, but this is governed by the genus of the fixed surfaces, and in 4 dimensions, that turns out to be quite strong and constrained. So we show that dull graphs are sufficient to, we show that equivariant cohomology is enough to reconstruct this dull graph. This doesn't quite get us to diffeomorphism. We do, the other thing that we do is we construct some examples. These two toric varieties, toric symplectic manifolds, with the circle action that restricts to just the vertical circle. These end up having the same dull graph. So the vertical circle, it has a fixed big vertex at the top and the bottom because when I restrict to the vertical circle, I have an edge that collapses to a point on the top and the bottom. And then we have 6 points in the middle. This dull graph sort of forgets the heights, so I just sort of have these points floating around. The dull graph does see, when I restrict to that circle action, I think I draw this on the next page. I do draw this on the next page, so I'm not going to draw this. There are some isotropy labels. These dull graphs have exactly the same, are exactly the same. We can see these two manifolds have different symplectic volume, so they're pretty much not they're pretty clearly not symplectomorphic. That's less surprising. The fact that they have the same dull graph means that they do have the same equivariant cohomology by this theorem with Kessler. And one thing that is true, they have different Chern classes. They have different first Chern class of their tangent bundle in that equivariant cohomology ring. Maybe that's what I want to say about those. The way that we prove this is, again, using this generators and relations description. These are generated, again, all in degree 2. They have some multiplicative relations, and they have, the thing that's different from toric is that the equivariant cohomology includes already some linear relations. That shouldn't be surprising, because if in the toric case, if you are restricting your attention from the full toric action, where you would have the Danilov-Jerkovich description, to get to a subcircle, you would project and you would have to add some linear relation, and that's morally what's happening here, because these spaces, these manifolds are all locally toric. We then went on to evaluate, these manifolds are not symplectomorphic, these toric varieties. They are not isomorphic as varieties. Oh, I should sort of explain to you what is the relationship between these. So if I look on the right-hand side of those pink lines, the things are the same. What happens on the left-hand side is that I have basically done blow-ups of, so I have a lattice points there indicated. The full lattice points sort of indicate a full CP2, and if I do a sequence of blow-ups, so I did that blow-up first, and then I did this blow-up, and then I did this blow-up, and then this blow-up. The blow-ups that I do are in a, this started with the same blow-up, but they are in a different order. And it's just the order of these blowups that changes, and it is, well, okay, so I've sort of done one upside down from the other. And what Liat and I joined up with Sue Tolman to prove is that even though these varieties are different varieties, as manifolds, in fact, there is an equivariant diffeomorphism from one to the other. And so this just this says that if you have an isomorphism between the dull graphs, then there exists an equivariant diffeomorphism between the manifolds. There are quite a few technical details. One of the things that surprised us a lot in proving this theorem, and maybe delayed us for 6 months to a year, was that at some point we were about ready to declare the paper done, and then we discovered something that symplectic geometers don't usually think about, which was an orientation reversing diffeomorphism of one of the very small examples. And so we had to make a long digression on orientation preserving and reversing diffeomorphisms. In dimension 4, there is an orientation reversing. So we don't normally think about these because we are so fixed on our fixed orientation, but there is an orientation reversing diffeomorphism of a four-dimensional manifold, a simply connected four-dimensional manifold. These exist exactly when you have the right Betti number, so B2 is 2. And so this is the case of S2 cross S2, and S2 or here it's 1. And so we spent some time trying to figure out exactly how those fit in. The other piece of this theorem is that the diffeomorphism that we produce, you can be very careful, and I mean, these manifolds could be abstractly isomorphic for reasons having nothing to do with the isomorphism of the dull graphs that you write down. But we prove a strong version. We say that if you have a specific isomorphism between these two dull graphs, then there is a diffeomorphism that produces that dull graph isomorphism when you apply the momentum map. And so there is this explicit diffeomorphism. It necessarily messes up the complex structure because, as I said, this is necessary because they are different varieties. And the consequence, this improves the following our equivalent statement of my theorem with Liat, which says that we now we have this four-way equivalence, and this question about inducing the dull graph isomorphism. So one can put the same sort of constraints in here. So two graphs are isomorphic as labeled graphs. Here, the isomorphisms of the cohomology rings should induce the isomorphism, the equivalent isomorphism of the labeled graphs. So this is in some sense strong, so you can actually find the right thing. And again, this is strong. You can find inducing the right isomorphism. And all of this can, let's see, so here the other piece is, so we have orientation preserving. We have orientation preserving here. And in the cohomology, you can, so these are statements about equivariant cohomology, statements 2 and 3. But again, you can ask whether an isomorphism induces is orientation preserving, whether it preserves, because these are all symplectic manifolds, they have a natural fixed orientation, and you can detect in cohomology whether that orientation is preserved, whether an algebra isomorphism is preserving the orientation. So again, there's a notion of orientation preserving in 2 and 3. Okay, so the moral of this whole story is that when you are in the complexity 1 four-manifold case, things are quite rigid. So everything is determined by the combinatorial momentum map data and isotropy data from the action, and everything can be detected in terms of the algebra of the cohomology. Okay, so that is what I wanted to say. And I think, as is our wont, we now have time to chat.
Thank you. Any questions?
Well, question, may I?
Yeah.
Yeah, so if I have a dull graph isomorphism, so could you give us an idea how you get this equivariant diffeomorphism?
Oh, yeah. Right. So that was this. So the dull graph actually, so for this example, let me go back to the dull graph isomorphism. So here, what basically happens is the only isomorphisms of the dull graph that you can have. So in the decorated graph, these chains of edges are oriented. So they go one, it's connected at the top on one side and to the bottom on the other. But in the dull graph, they're just sort of floating. And the idea is that to produce the idea is for each of these chains, you can orient them up or down. And this is the sense in which orientations start playing a role on the dull graphs. And then the algebra isomorphisms and the dull graph isomorphisms that you can find basically have to do with flipping those chains up and down. And so the diffeomorphism that we find, we basically have to find for a single flip a diffeomorphism that involves dealing looking at the chain of blowups that gets you that chain, and then writing down very explicitly in coordinates a diffeomorphism that turns the blowup upside down. And that I don't think I won't be able to write it down correctly on demand, but it's written very explicitly in the paper, and that's all that it's doing is sort of pulling it upside down. But you can also see, I mean, we write down functions, and you can precisely see how they mess up the complex structure. So it just involves blowups and understanding equations on the blowups.
Thanks.
Sorry, can anything be said about higher complexity cases?
That is a very good question. The short answer is I don't know. A lot of this relies on this generators and relations presentation. That's how we understand the algebra, the generators and relations presentation, and how that lets us really get a strict hand on the algebra. In higher dimensions, I don't have any idea about how to, although I think Liat and one of her postdocs are working on how to extend that, but I don't quite know how it works.
Thank you.
Another piece, everything that I've said is about smooth manifolds. Another piece, another direction that I've been thinking about lately is what can you say still in 4 dimensions, but instead of manifolds, think about orbifolds. And I'll advertise, there's been some very nice work by Leonor Godinho, Grace Wakayama, and Daniele Sepe on Hamiltonian circle actions on 4-dimensional symplectic orbifolds. So that work is very beautiful, and I've been talking with Leonor and Daniele about what we might be able to do combining forces with these two types of tools.
Okay, so is there no further question? Let us thank Tal again.